Hi everyone. Today I'm going to discuss about how the backside power delivery is helping in the chip design to reduce the IR drop, that means power dissipation in the chip, and improve the performance and even improve the signal integrity between the signals in the design or in the chip, like how it is helping throughout the chip. I'm going to discuss on this more in my coming slides. So coming to that backside power delivery network, we'll call it as a ABS-PDN. It's a technology currently adopting in the 2 nm below of that 2 nanometer below that technologies. So it's a revolutionary because earlier we used to have that whole the power delivery on the front side of the design along with the signals. So suppose like if you have the metal layers of 15, then the top metal layers will go for power and the next metal layers will go for the clock and the remaining metal layers is go for signal. So because of that we can't use all the metal layers for the signals, and there is no availability of the for the routing resources for the signals. Because of that we moved that most of the backside, most of the power routes in the backside through nano through silicon vias. We are making like a reducing the stop state of the chip, and we are putting like a sending the vias through that to connect that backside power. So it's a revolution in the chip design, currently adopting like many of the lower level nodes like Intel, TSMC, and Samsung. This actually earlier, as I mentioned, the power and signal are in the inside of the design, but here we are moving that entire power into the backside of the design, and we are using like connecting this one to the TSV. This is helping like a significant improvement in the performance, efficiency, and power. So this incorporates like an another silicon vias for direct power delivery through silicon substrates. We are thinning like silicon substrates. Silicon substrates means it's a CMOS device. There's a substrate in the CMOS device. So we are making like as much as thinning because of to connect that backside power with the front side of the design, integrating that front side of the design with the through silicon vias. So reduce routing congestion, IO drop, improving that signal integrity. Intel's power via implementation and further developments are going in the other manufacturers like TSMC and Samsung. So I'm going to discuss more about on this in my coming slides. So if you're coming to that traditional power delivery limitations, there's a routing congestion in advanced 5 nanometer and below. There will be like most of that 40% of routing resources is consumed by the power delivery, and remaining goes to the clock and signal. As metal pitch are scaling down in the lower technologies to 24 nanometer, higher drop increasing domestically by 45% compared with the previously technology nodes. So it's a severely constraining the signal routing options because we don't have the routing resources for the signals. So for this, we are moving to that the backside power. And also there is a other disadvantage, voltage degradation. Like the technologies are going down, like we are going towards the 2 nanometer. So the operating voltage also will come down now like 0.7 volts, and voltage drops also significantly 12 to 15% across the die during the high competition loads. Even like in the critical corners it is increasing like 16.5%. So this is like another disadvantage with the front side. So there is a power supply noise. Currently the dynamic power circuit operation generates a substantial power supply noise reaching 85 to 95 millivolts peak to peak under typical workloads. This is a regular normal power domain supplies, and impedance fluctuations at 22% from nominal values, signal integrity and timing predictability. So this backside power delivery architecture, how it will be, the as I mentioned earlier, the vapor processing, we are reducing that substrate as much as less possible to make it like to get high yield, along with that with better yield and reducing that substrate. So precision substrate thinning to 12 to 50 micron thickness with exceptional warpage control maintained within 45 micron across the 300 millimeter wafers. Advanced nano TSP fabrication achieves remarkable aspect ratios of 10:1 in the backside power delivery. It's featuring like ultra fine via diameters 100 to 200 nanometer and precise depths exceeding to 2.5 microns. So power level implementation specialized backside metal stack utilizing advanced copper metallization techniques achieved use ultra low shear resistance of 0.015 ohms per the engineered three-layer power distribution network with optimized 4.2 micrometer thickness delivers substantial 58% reduction in the PDN implements compared to conventional approaches. The system benefits significant reduction in required metal layer from conventional 10 to 12, like 10 to 15 even metal layers. Now it is we are moving to 7 to 8 for the same frequency. So our signal interconnect length decreases by 25% and directly contributing to the dynamic dramatic RC delay improvement of 35% while simultaneously reducing signal crosstalk by 42% because of more routing resources available for the signals. So it improves the performance and reduces the dynamic power as there are more vias for the power and more routing resources available for the signal, there will be less crosstalk. So if you are comparing the performance between the traditional power delivery network and backside power delivery network, the wire resistance is traditional it is like 150% and backside power it is 100%. The power consumption watt for if you are comparing with the watts per millimeter square, then it is 2.5 in the conventional and 1.75, and metal layer says it is 35% and 15% in the backside power delivery. PDN resistance it is 100% and 55% IR drop it is 100% in the if you are comparing with 100% then it will be like 45% with the ABS-PDN. Metal layers will be come down. It is if you are getting with the 8 in the traditional and it will be like 3. So while manufacturing we have to consider these things: wafer thinning, ultra precise thinning up to 5 to 10 microns with exceptional surface integration below 2 nanometer or mesh roughness. TSV integration, high precision 500 nanometer TSVs featuring industry leading 10:1 aspect ratios with the near vertical 89.8 plus or minus 0.2 degrees sidewall profiles, and the thermal management. Strategic TSV placement architecture reduces the critical thermal gradients by 40%, enhancing the device reliability. So these are like the helping the we have to consider these while manufacturing for the backside power delivery. So design methodology adoption. So machine learning optimization, 65% reduction in design cycles with 45% improvement in power delivery network efficiency. Advanced simulation tools. If you go with the 3D electromagnetic analysis, achieving like it's a 94% correlation with the whatever we get with the actual silicon post silicon measurements. Power gate design, like best TSV placement algorithms will reduce like the IO drop, voltage drop by 48% across critical paths. The most of the leading companies are adopting this backside power delivery currently. So this will reduce like the thermal dissipation and improves the current density across different multiple designs. The runtime also with the advanced tools, the runtime will be increased by 70% improvement. It will accelerate the time to market of the designs. So these are major players currently adopting the backside power delivery. Intel Power VIA. Currently, Intel is adopted 18A node. 18A means 1.8 nanometer. This is the Intel latest technology. It is equivalent to this latest technology. TSMC not yet come back, but Intel is working on this 1.8 nanometer. So first adopted in the Intel technologies, Intel latest technologies. It's achieving like a 30% power delivery efficiency, and the current improvement also it's at 2.8 amps per millimeter square while maintaining like a plus or minus 4% voltage regulation across the day. TSMC has invested like the 2.8 billion on this backside power delivery. They are working on this. Demonstrate exceptionally like 28% power efficiency with they are predicting, and with the 15% performance improvement in the 2nm process nodes. Samsung also adopted this one vertical power delivery with the TSVs 150 nanometer diameters with the same 10:1 aspect ratios of TSVs. Advanced metallization techniques yield 2.2x electromagnetic aggression resistance compared to traditional power delivery architectures with this Samsung technologies. So future aspects 2025 and beyond, I said 25% market adoption in the 2025, predicting for the high performance computing and mobile applications. It's at 25% predicting will adopt this backside power delivery with the latest advanced nodes, and a market opportunity is like 8.5 billion for the technology integration across semiconductor sectors. 40% efficiency improvement, power efficiency gains in the next generation chipsets utilizing advanced ABS-PDN architecture with compared to that conventional front side power delivery. The current density, it's 4 amps per millimeter square, peak current handling capacity while maintaining precise plus or minus 3.5% cross voltage regulations. Advanced research institutes are now accelerating towards breakthrough BSPDN implementations with unprecedented specifications. Leading teams are developing ultra miniaturing TSV structures with diameters below 100 nanometer and revolutionary 12:1. Currently, like we have the 300 nanometer and 200 nanometer TSVs. So they are working on to reduce that diameters to 100 nanometer and aspect ratios of 12:1. It will improve the width and depth of that vias, and also the junction temperature beyond and improving that current density. So the work is still going on this. So performance metrics across manufacturers, for efficiency improvement, Intel leads with a 30% improvement, followed by TSMC 28% and Samsung at 25% with their backside power delivery implementations. TSV yield rates through silicon vias, Intel achieves highest manufacturing precision with 99.95 TSV yield rate, while TSMC and Samsung follows by closely by 99.8 and 99.7. Current density, power via technology enables like Intel to reach 2.8 amps per millimeter square. The Samsung and TSMC just lagging on this, just below. Temperature reduction, all manufacturers choose significant cooling benefits with Intel reducing temperature by 8 degrees centigrade, TSMC and Samsung 7 degrees. The comparison is performance metrics for the backside power delivery. Feature implications, density improvement, implementation achieves transit density improvement also along with the performance improvement. Compared to traditional power delivery, it is like 25% improvement with the traditional power delivery network. The power is reduced by 35 to 40% with the different metal layers. Performance enhancements, overall performance efficiency improved by 20-25% with the dynamic power reduction, 30% in high performance computing, data measurement, and 35% only. Design flexibility, separation of power and signal domains enables 35% reduction in routing complexity. It will reduce the routing resources with the average wire length also will come down to 20-25% required metal layer reduction from. It will also come down the metal layers, right? Into instead of 12, we are going with less metal layers, 78 for the same functionality, 8% to 18% delay reduction. Economic impact and conclusions. Initial cost of this will increase 18 to 22%. Return of on investment timelines will be like 15 to 12, 20 months for data center implementations. Yield improvement 80% higher than conventional process. Design cycle is at 25% reduction in design cycle environment. Cycle time. This is as a advanced technology. Currently, most of the lower technology nodes we are adopting in the lower technology nodes in the chip design. So for the to reduce the power and improve the performance and reduce the signal integrity issues. So thank you for listening. Thank you very much.